Hi, we're going to develop a 3D simulation of a projectile motion using the Babylon.JS library that is a game engine for developing video games in JavaScript to run them on the web browser. And we will need a simple theory about kinematics and calculus so that we can model our motion for the particle. You can see the animation is running in the web browser, and we have the particle that has a motion described by a quadratic curve. So this is what we're going to develop by following the article for this project. I'm going to give you a bonus about a project that I was working this year, and it has to do with this kind of drawings. We're going to see it later, but first I will suggest that you should read and follow the other articles that I recently published about Babylon.JS. There are two articles, and the first one is about creating cubes, and you can check here. The result that you will get is something pretty simple. After modeling a cube, you will get something like this, a box that has 6 sides, and it is a 3-dimensional model. And then you will be able to position many cubes into the XYZ position that you want to use, and add other properties like color. For example, the next article is about populating a random dice. So a dice is basically a cube or a box that has 6 sides and 6 numbers from 1 to 6 inclusive. So here I have a reference to a playground where you can go and check out, and you get these dice, but these dice are always the same when you generate the dice. Here we want to generate a dice that is randomly generated each time that we run the application. So after, as you can see here, the unique function, this arrow function generates a unique number to get the side of the dice randomly, and so in the end you will get this result. If you run the application several times, you will get a random dice because we selected the sprite that is part of each of the side of this dice randomly. We selected that sprite randomly, so we will get the dice differently each time that we run the application because we will be applying this arrow function before. So those are good examples, and you can go to the playground as I said before. You can see here, and then you have to change this behavior, so each time that you run, you will generate a randomly labeled dice. So after following those two articles, then you will be able to understand this third article that consists of an animation that is not too simple, but it is not too hard, or is not too elaborated also. But you have to understand how to work with Babylon.JS before. It is a JavaScript library that you can add via CDN or npm, any way you like. So to get started, I will mention right now that we will need some code for our project to draw a line. You can see here the trajectory for this particle is a quadratic curve. So we're going to draw the slopes for this curve, or the tangent lines, or the secant lines that passes over each of the points that until we get all of the curve graph into the plane that we're going to use here. So we also need lines to draw the axis, the y and t axis this time. Remember that we're going to use time as the independent variable for this problem. So to draw a line in Babylon.JS, you just copy this line to the function that is given here in the documentation, this function. And you can see here the playground has some lines, so you can check out. So this is the code that I use. It is actually a lot of code just for drawing a simple line in 2 dimensions. Remember that Babylon is a 3-dimension game engine. So to get started, I'm going to open my IDE and I will be working on the tutorial here in this package tutorial. And so it is a web project, so you will need an index.html file to start the application, an index.js file to add the logic to the game or to the animation or simulation, the lib.js, which will contain the code that I said before. So I'm going to add this code to the project. And reference here to the source where I took the code. Then we will have this function here that is going to be useful. And to get started, as I said in the beginning of the video, you should have followed the other 2 articles about the Babylon library. So I'm going to copy a basic structure to initialize the application that I used with those 2 articles previously. So to get the initial structure, I will use basically the same code for the HTML file. You can see we have to import via CDN, or you can create a npm project to add the library also. But it will be okay if you add the CDN here to import the script, the Babylon.JS library. Remember to also import the lib.js file that contains the function that we're going to use to draw a 2-dimensional line. and also the script that we're going to use to develop our game logic. We will also need to import the style.css to give a better looking way to have this application. So I'm going to copy the style that I used previously into the first and second article to update the styles.css file. And I'm going to run the index.html file, so we can see here that is the basic structure. Now we can focus on the index.js file. That is what actually matters. First of all, I'm going to add from the article again the basic structure for the logic of Babylon.JS. As you should know, all of these kind of game engines have pretty the same steps to initialize them, like adding camera, light, and setting up the scene. So you can see here, first I will register the DOM content loaded event to initialize the elements, and also define some constants for the width and height of the physical canvas that I'm going to use. It is where we will have the axis plotted and also some position to draw the axis so they can be more centered. To initialize the application, just get the canvas element and create a new instance of the main object that is returned by the main function and call init. The main object is like the controller for our application. So this is the basic structure that I have used for the other project, the other two articles. So this is basically about Babylon.js. As you can see here, the init method creates a new engine, scene, and camera, initialize them, and the render loop is run so that we can render our scene on 60 FPS. And we have the method to prepare that logic to create the camera, scene, and the engine object. So our main code is here into this main function that gives us the instance of the main object or the controller. So now we can check the result. The canvas is drawn here. We have our canvas here and it's empty, but we have an initial structure for the styles, the HTML, and the JavaScript file. So now we can start adding the logic for our animation. First of all, we want to draw the axes. The axes that are going to plot the position versus time plane. So I'm going to add this function over here. to draw a new axis to draw the two axes, and they are the x and the y and x axis. Actually, this should be t axis, but it's okay. We know that our independent variable is time. So first we have to use the line2d function that we imported before to draw a line. As you can see, the y-axis doesn't change, is x position, and the x-axis doesn't change, is y position. So it is a vertical and horizontal line respectively for each of the axes. So we can call that here. And we have the result. We have two lines that look like a plane for the axis that we're going to use. And as I said before, we will have a physical size of 160 pixels for width and height that we will have to convert into domain values for our models. And this is an important point to take into account. So next I'm going to address two things. One is the bonus about the axis that I said at the beginning of the video. It is about a project that I was working this year. And then we will talk about the model that we're going to use regarding the equation for the motion of our particle. So here I have an article that I recreated before this year, and it's about drawing a tree on a bare HTML5 canvas for drawing the solution tree for the machine replacement model of the website mode solver. And what all this means, I haven't published this article yet, but I already created. So you should keep in touch to get the article when I finally publish it. And the reason is because it is one of my premium or first class articles, so it's very important, and I'm going to publish it later. As you can see here, the machine replacement model is a problem for operation research, and the solutions, all of the possible solutions and the actual solutions that are computed by the model can be represented into an XY axis. Just take that into account. What we want to draw here is an XY axis and a tree that is graphed into this plane, where the y-axis is the machine age in years, for example, and the x-axis is the decision year, which is my independent variable. So I have time here, and I have the machine age on the y-axis, and then I have nodes that correspond to the xy position. So for example, I have a machine that is 3 years old, and we have here the first decision year. So what do I want to do with that machine at the first year? I want to keep that machine, so the next year is going to be 4 years old. Or I want to sell the machine and buy another one, a new machine. So the new machine that I'm going to have next year is going to be 1 year old because it's new. So this is the solution scheme for this problem. So we can see here that we have an XY axis, and the solution tree is drawn here. But this is the first implementation I made way before 2019, and it's just bare HTML with CSS. I'm using an rectangular model of coordinates to draw the XY position, but the problem is inherently recursive because it's a tree, and trees are data structures that are recursive by its nature in mathematics. So I changed the model lately to make a better representation of this solution that is state of the art. That's important. So we can see what we can do with this kind of drawing. In this case, I could have used Babylon.JS, for example, but we will have many other options that are available to employ. So basically, I was developing this really good problem, the implementation. So of course, we have here what we care the most is the white matters. And an implementation for drawing. This is not easy actually because I have to do many things and take it into account, and even when we take the performance into account, it's even more complicated to solve. In JavaScript, in this case TypeScript, is not a good technology to solve this kind of problems, but I have to solve them into web technology by using TypeScript for now. So you can see here with some code by using the native HTML5 canvas. You can see here in this code, I drew the X label, the Y label, in an imperative way, the two lines to get the axis. So you can use the canvas element to draw it, and it is pretty similar to the Java 2D API or the HTML5 canvas API. These are pretty similar when drawing 2D objects, but of course Babylon.JS or other libraries or frameworks like Play Canvas that I was looking before, for example, are meant to use WebGL to render three-dimensional objects or models, so we can get video games but in this case I only care about two-dimensional plane, while here we have a plane into a three-dimensional space, so we can see here. So you can see here how I was able to draw this axis, the Y and X axis, and also add the labels for the values that they will have. And so we want to check the final result is pretty compelling. Okay, I will show you the actual application instead. You will be able to read the article later if you stay tuned. I performed some results here, but basically, and I also had to use mathematics, basic trigonometry and mathematics to get some computations to properly position some labels, for example. So here I have the Simon solver installed. And as I said, this application is state of the art. This example that I just loaded is the example from the book. And the book has an error, and I have spotted many errors on papers and books because I have the solver. It's pretty easy for me to know when they are wrong. So you can see I can add the model. Okay, I'm going to load it and add the corresponding information for the problem and solve it. And we can see the result here. So according to the model that I gave to application, I will get the corresponding solution space into this compelling visualization. This model visualization, we can see the change from the first version to the latest one was really good. I have a pretty decent rendering of the problem, and after computing the model by using recursion, by the way, we can see that the result, we have two bifurcation with two results, this one and the other one. That is basically, we have first replace, and then we have two possible options, keep, but from here we can either choose to keep or replace, because it gives the same, it's the same, in this case, it's the same value that we're going to get whether we keep or replace. It's mathematically the same value, so we can choose either or any. So we have a bifurcation here, two branches, and that's why we can see here that it's dynamically rendered. We choose to replace, and then we can choose to keep or replace. Is optimal, and we can see the rendering here. And as I said, this is not quite simple to render because of many constraints that we will have for correctness and performance and for modeling. So I show all of the possibilities that you can have here, but also the solution that the solver computed in the same graph. You can see. Okay, now we have a really simple problem compared to the previous problem, and we're going to solve it. That was just to give you an insight about what can be done with this kind of simulation or models. So now the next step is to get the model for the motion. The reason why I chose this function, you can see here, it's important to take into account the equations, because the equations are the source of truth. And first I will have the acceleration vector that has magnitude g, where g is the gravity value and is in direction of the unit vector j to the center of the earth. So it's negative acceleration, and by integrating we can easily get the velocity vector and apply an initial speed vector v sub 0 for the integration constant, and we can integrate that again to get the position vector. So we have the popular equation minus 1/2 gt squared in direction y plus the initial speed times t. So this clearly corresponds to a quadratic equation, and by removing the parameter we get that x of t equals t and y of t equals minus 1/2 gt squared, and also taking account that our problem is a two-dimensional problem. So I remove the parameter, but also assume that we won't have a third dimension component. That is, I remove the z component. So this is the equation that we're going to take. What we can see here is that it is a quadratic equation, and as I said, our graph is going to be y position versus time. So is position a function of time? We can choose a quadratic equation, but we have to choose an initial speed to get our curve. So to understand this, I had to choose wisely a quadratic curve that is going to be useful for this exercise, because our plot is not too accurate. to draw something too complicated. For example, if I choose a wider domain from 0 to some other value to 5 to 8 to 10, the maximum value of this function is going to be too wide and it's not going to be easily readable here when watching the animation. So a good value for this exercise is a domain from t equals 0 to t equals 4, so that the intersection of the curve has to be at 0, 0 and at t equals 4. And we also have a good value for the maximum point at t equals 2 and y of t equals 4, because we only have a 4 by 4 grid here, 4 by 4 units that we can employ to render the curve. If this maximum point was much larger, it wouldn't be too feasible to draw, so it is something about convenience. And I also advise to understand the equations, because that's how everything can be inferred. So here, for example, I give the derivative or the velocity of this position function, that you must be able to understand it by just watching the curve. Being able to understand all of this information is really necessary, because it shows your understanding of concepts like limits and calculus and derivative. That is what I used to do before when I was learning calculus 1, for example, to really understand what I was reading on the books and develop my cognitive way of developing all of this kind of computation, that as an actual engineer you have to be able to make them in real life. So you can see here the derivative is 4 minus 2t, but it must be clear for you that, for example, at t equals 2 is the maximum point of the function and the derivative is 0 here. By making 0 the function 4 minus 2t, you will get t equals 2, and so y equals 4. And also, without seeing the derivative function, you must be able to know that the derivative of this function is negative from t equals 0 to t equals 2. Okay, it's positive and is negative from t equals 2 to t equals 4, because it's increasing into this interval but is decreasing from the other interval. And it's clear that at t equals 2 the derivative of this function is a stationary point, so this derivative is 0. Okay, after selecting our model to create the animation, we will just add another piece of code to make this done. I will need a function to to compute the value of the quadratic equation, as you can see here. That is going to be our model. And then I will add this other function to draw the curve that I was talking about. So as I said, the domain is going to be from t equals 0 to t equals 4. So we have here a logic to render the segments of the lines that are going to create the curve. So I choose a step, how many steps I want to use. The more steps you add, the more accurate is going to be the representation of the curve. And then we will need other functions for transforming the physical values into domain values. So I'm going to add these other functions here. It's just to transform a value in pixels to a value in domain. Our domain values are from 0 to 4. Is the logical value that our function or model is going to take, and the pixel values are the ones that are going to be drawn into the canvas, and the other way around by converting the domain value to pixels. So here we can draw the curve by getting the domain value from each iteration that we're going to do. For each step size that we computed, we will have a step size, and we get the image of that value by calling the function that we define here. Is the quadratic equation that represents our motion, the position of the particle. And so I'm going to compute a value that is a delta from the current value to the last value that is going to have the step for the segment of the line. And then draw a line from the initial point t, y, and that goes to the end value. So I'm going to draw the curve here. I have to pass this in. And I will also need a constant that is going to tell us about the maximum value. Okay. That we can see here, we used to convert the domain values to pixels, and the pixels to domain values is the maximum value that we're going to have. So we can see the result, and we have rendered the curve via these segments of lines. And actually, you can see I took the image of the curve at point T, and also the image at point T plus the step that we defined divided by 2. So I took this starting and ending point of the curve to define the segment of the line that is going to be drawn. That is the second line. You can also get the derivative at the center of the point and draw the tangent line by taking this segment, but it would be a little bit more complicated and it's not necessary. So I took the second point and it's alright. So we can see here the representation of the curve. If we limit the step that we take, we can see a less defined curve with only 4 steps, but it has the idea of the curve. So we get it. Now I'm going to draw the sphere so that we can continue with the animation. For drawing a sphere, I have to create a mesh that is a model that has our values, and via this constructor create capsule, and I can assign the position where I want to draw it. But as you can see, I'm using a state model here, so I'm going to add the code to define that state. This state is the logic for the animation, and it consists of an accessor for getting the physical position in pixels of the particles. As you can see here, I have the domain value t for the current state, and we can get the position by transforming the domain value to pixels. And then a method that is going to be called for every tick of the game to update the model. Then I'm using the performance API that is standard for running benchmark in JavaScript for web application running on the browser, so I can measure the current time. For each tick, I get the new time, this line, and then I can compute a delta in seconds. That is the time that is computed from the last tick to right now. So because t is our independent variable and is time, we have a direct way of relating these quantities, because I'm getting the delta time, so I can run actually in real time the animation. So that is exactly the value that I'm going to use to date the t value. That means that if we wait 2 seconds in real life, then for the animation or the simulation it's going to be 2 seconds. If we wait 4 seconds in real life, for the animation it's going to be 4 seconds, and the particle is going to be to the end of the curve. And that's basically it. And then just add some logic to check if the value of t is out of bounds. You will have to change the direction so that we can have a endless animation back and forth. And if the value is out of bounds, still we have to place it into a correct value, because the particle can be stuck out of the bound from the domain that we define from t equals 0 to t equals 4. So we should validate this logic so that our particle is always on the right domain that was defined from t equals 0 to t equals 4. And so it won't get stuck anywhere else when changing the direction, for example. This is the state that is going to be used, is the main logic of the animation. And then we can make use of that state. I'm drawing just a sphere here. So I'm going to update the main loop with the final code. Remember that in Babylon.JS we have a 60 FPS rendering that we're using for getting this animation done. So here we have the final animation. And I only updated some parts of the code. As you can see here, I added a last mesh variable that we're going to use later. I created a state instance that is going to represent in real time the position of the particle, where the position is going, is our model. The other things that we already had, and here you can see I'm calling this function base draw to draw things that are not going to change a lot, like the axis and the curve is not going to change with the animation, and this might be useful for performance reasons. We don't need to draw every time these two things, the axis and the curve, because it's the same. The object that is moving is our particle, so that is what we're going to update. And after calling this, the render loop is going to be called 60 times per second, and so we can invoke our draw function that is going to update the GUI or the game. Okay, if I don't add this code, we'll see what happens. The last object or the last particle that was drawn here is not removed, is not clear. Okay, so I had to save the last mesh to dispose it this way. So after one tick, I can remove or dispose the last particle that was drawn, and we clear the state. I tried to use the clear function, the clear attribute here, but it didn't work. So I employed this method to remove the last mesh or the last sphere that was drawn, and so we have the animation clear. Then the last mesh is just a sphere that I generate from the state that we have, and as you can see, I'm calling the next state method from the state object to update the logic of the animation or the state of the particle. So with that logic, we can get the final animation. So now we can say that we employed Babylon.JS and web technology, and also equations that are really useful and popular for the motion of particles that you can see in basic kinematics course. and so we were able to develop an animation that describes this particle position in one dimension over time. You can read the article for getting more information about it, how I created all of the process and all of the resources that are necessary to complete this project. It is really recommended. I advise a lot to employ all of these physics and theoretical or mathematical concepts in real life. That is what makes you a better engineer.